This video is about the assumptions of within subjects designs. Within subjects designs are designs where each participant is tested under multiple conditions. So each level of your independent variable, where your independent variable is what establishes the groups that are being compared when you're doing mean comparisons in ANOVA. But within subjects designs is that every single participant is in every single level of that independent variable. And this is what the equation looks like for this type of model. Very similar to the between subjects designs, but slightly different based on the variances that are being used. These within subjects designs are also called correlated error models, but the one that you would most likely hear is repeated measures designs, or this is can also sometimes be called longitudinal ANOVA. So this goes by several different names. But regardless of the name, the biggest point is that every participant is in every level of your independent variables. So each participant is in each group. So now your ANOVA is more like a paired sample t-test than an independent sample t-test. So for the between subjects designs, you have independent groups where the participants in each group are only in one group. Whereas with now the within subjects design, it's like a paired sample t-test where we use paired sample t-test for like a pre-test, post-test comparison. And this is where every participant is in both groups. It's both in the pretest and in the post-test. But now we have 3 or more of these groups to be able to do this within subjects designs ANOVA. And so the subjects are providing multiple values for the dependent variable. And so for each level of the independent variable, each participant will have a value for the dependent variable. So the means of the dependent variable are still what's being compared across the groups, just as in any other ANOVA design. But now you have each participant is at every level of the independent variable. And so this repetition can be over time, and most often we see it over time. So it's 3 or more time points where each participant has a value of the dependent variable at each of those time points, but it could also be over treatments where it's like a leveling or a stacking of treatments, or it could be something where it's the increase of sessions, so the number of sessions, but you are measuring the dependent variable at each session. So then session 1 dependent variable value could be compared to session 3 dependent value and look and see if there's mean differences across all these different treatment levels. So we first have to think about power for this type of design. So for within subjects or repeated measure designs, the power is still calculated similarly as between subjects designs, but all the assumptions must be met in order for this power calculation to be the same. And so if there's assumptions that are violated, then it's changing the contribution of the sample size to the calculation of the power. And so you get an underestimate of the sample size that's being used, and you get an overestimate of the power that is obtained. And so you have to make sure that you are meeting the assumptions of within subjects or repeated measures, models, and designs to ensure that your power calculation is accurate. So the assumptions for a within subjects design are the same three as with the um, between subjects designs. So independence, multivariate normality, and homogeneity of variance, all of which are particularly focused on the error or the residual term that is part of your model. But you also have this new one that's called sphericity, and it goes by a couple of different names. Um, and it's been called circularity, but it's related to compound symmetry. So compound symmetry and sphericity are not the same thing, but they are related to each other, and they both are important in thinking about this new assumption. And so sphericity is really looking at, do you have equal variances between the paired levels of your independent variable? So for your within subject designs, you are comparing every participant to themselves at different levels of the independent variable. And so whenever you are pairing up, so in the computation, whenever you're pairing up any two of those levels, they should have equal variance. This way, we know for sure that the differences we're seeing between those two levels is the mean and is not from a difference in variance initially. So compound symmetry is related to sphericity, but it's a little bit different, and it's actually a stronger statement than sphericity, because compound symmetry is looking at the equality of the variances and the covariances, whereas sphericity is just focused on the equality of the variances when we are pairing up any two levels of the independent variable, whereas compound symmetry is also looking at the covariances between those two pairs and essentially making sure that you have equality of variance and that their relation is clear. And so we tend to use tests of compound symmetry to test the assumption of sphericity. And this is because repeated measures or within subject designs are not robust enough to overcome a violation of sphericity. So if you have a violation of sphericity, and we use compound symmetry to make sure that we are being stringent enough in our tests to find any violations, if you do violate sphericity, your F is now shifting to the right, and so your central F values are going to be too small. And so essentially it's throwing off your F ratio and the determination of statistical significance based on the comparison of the non-central and the central F values. And so there's two different tests that you could use when testing sphericity. There's actually several different tests, but these are the ones that are most commonly used. So if you do have a violation of sphericity, there are a couple of options of things you can do, but it's pretty difficult to adjust for a violation of sphericity after the data has been collected and the initial analysis has been run. You can do an adjusted ANOVA where you are adjusting the degrees of freedom, which in turn adjusts the p-values and the type 1 error rate. So you could do that and make this adjustment, or you could switch to doing a MANOVA, or you can have planned comparisons. But you have to remember with your planned comparisons, these have to be planned ahead of time. So if you are worried about having a violation of sphericity before you collect your data, you should plan what planned comparisons can be done instead of or in lieu to there being a violation of sphericity for your whole within subjects model. So one of the options if you have a violation of sphericity is to do an adjusted ANOVA, which is an adjusted degrees of freedom. And so how you do this is you do your F-test as usual. And if there's a violation of sphericity, then you stop. If it's significant, then you use the most conservative test, which is the lower bound test, with the least degrees of freedom. So this would be the most stringent test you could do to be able to look at your values. If the low bound test is significant, then you stop. If it's not significant, then you have to use a more powerful, less conservative test. And this is where that greenhouse geyser with adjusted degrees of freedom must be used. So again, if you have this violation of sphericity, you can use this geyser greenhouse to be able to make adjustments to your degrees of freedom. But if it's significant, you have to stop. If it's not significant, then this greenhouse geyser is overcorrecting, and you have to go on to the Hein-Feld test, which is an epsilon adjusted degrees of freedom, but it uses a completely different formula that is